Okay, so the question is, the figure question number 1C shows a closed loop unity feedback system with a PID controller, proportional, integral and derivative. PID controller, right? And G is the transfer function of the PID controller, GPID, and G of S is the plant, and this is the closed loop diagram of a unity feedback system. The open loop transfer function G of S is 10 over S cubes. This is S cube. This is a typo error here. This is S cube plus 9S square plus 23S plus 15. Okay, this is a third order system. GPID is used to control the system using Ziegler-Nichols tuning method. This is ZN method. This is very popular method for tuning a PID controller. Referring to the ZN table in the appendix A, determine the following: the ultimate gain and the ultimate frequency. First part. Second part is controller tuning parameter using P controller, proportional controller, and third one is the controller tuning parameter using a PID controller. So before proceeding, I would like to revise a bit this tuning method, in which first of all we will set this controller G as a simple proportional controller, like G of S will be equal to simple equal to Kp or Ku, you can say Ku, ultimate gain. Ultimate gain is the gain which is, if we keep on increasing the gain, we will get one gain at which the system will become oscillatory. The system will become oscillatory or undamped. So that gain at which the system will become oscillatory, this gain is called ultimate gain. And if we measure the time period of this uh, oscillatory system and determine the frequency, which is f is equal to 1 over t, we will get the frequency by 2 pi f or 2 pi capital T. So this will be the ultimate gain, and its table is shown. This is the table of the Ziegler-Nichols method. We will determine the Ku and Tu. Ku is the ultimate gain and Tu is the time period. Okay, okay. So after getting Ku and Tu, which I will show how we will get this, through classical control method. We also do this practically in the industry. We keep on increasing the gain, proportional gain, and at one value of the gain the system becomes oscillatory. So that gain is called the ultimate gain. Now in the questions, how we will determine this? We will determine this through the Routh-Hurwitz table. Like we will make the Routh-Hurwitz table of this closed loop system with only proportional controller. And by theory, if one row of the Routh-Hurwitz table becomes 0, the system becomes oscillatory. Its poles lie on the uh, j omega axis. The poles will lie on the j omega axis. Because of the oscillatory system, we have 0 real part, but imaginary part, some imaginary part. So coming back to the question, okay, now this is the 10 over s cube plus 9s square plus 23s plus 15, and this is your k. So first we will make a unity closed loop transfer function. How we will get this, I show you. So this is basically g of s 10 over s cube plus 9s square plus 23s plus 15. So g of s is equal to 10 over, okay, 10 over s cube plus 9s square plus 23 s plus 15, right? 23s plus 15. Okay, so for the closed loop controller we have the controller gpf is equal to k, you can say ku. So the closed loop transfer function t of s will be equal to your gp of s u of s over 1 plus gp of s u of s, right? So you put here these values, you put here in this, you will get here, sorry, so we have to multiply first these things and then 1 over 1 plus again this thing, so this will be 10. So t of s will be equal to the multiplication of these two, okay, and then 1 over 1 plus this thing, so 10 into k over s cube plus 9s square plus 23s plus 11, right? Sorry, 15, it's 15, so it will be 1 plus 16k over s cube plus 9s square plus 23s plus 15. So we move these two here and this will get cancelled with this thing, so we will get only this 10k over s cube plus 9s square plus 23s plus 15 plus 16k, sorry, it's not 16, it's 10k. Let me check this. Yes, it's 10k. Okay, now this is the closed loop transfer function t of s and this is the denominator, right? We will make the root Hurwitz table of this s cube plus 9s square plus 23s plus s raised to the power 0 15 plus 10k. So root Hurwitz table, how it is made? Root Hurwitz table, it is made like this. See here, it's the root table. Yes, so this is how we will make it a root table. Okay, so here you can see that first s raised to 4, s plus 3, s square, s1, s0. So a4, then we have to place a2 and then a0. After this at s cube we have to place a3, then a1, then 0 because there is nothing ahead, and s square, how we will make it? We will make it minus 1 over a3, okay, and then the determinant a4, a3, a2, a1, okay, this will be called as b1. Similarly this one, that is minus 1 over a3, a4, a3, and then a0, a0, this will be the determinant column, this is b2. And a3, how we will get is minus 1 over a3 and determinant of a4, a3, 0, 0, okay, this will be 0 because if we multiply this upon the determinant we get the 0 answer. Now at the s1, how we will get this? We will get this by this a3 over b1, a3 b1, and then a1 b2. This will be the determinant elements, and minus 1 over b1, that is minus 1 over b1, a3 b1 a1 b2. Okay, this is c1. And here how we will get this? Minus 1 over a3 b1 and then 0 0, we get 0. Here minus a3 b1 0 0, and we will get this will be 0. And how we will get s0? These coefficients will get from these two, the upper two rows, minus 1 over c1, then b1 c1 b2 0 here in the determinant. Similarly here minus 1 over c1 b1 c1 0 0, and here minus b1 c1 0 0 here. Okay, so this is how the roots table, we have to make the root Harvard's table, and we have to make one row fully equal to 0. If we make one row 0, that means we will have the poles on the j omega axis. This will make our system oscillatory, which we do practically by increasing the gain, and this is the theoretically how we will do this. So coming back to the question, this is the root table which is formed now here.
Doctor, I had like a question.
This you can see that if the poles lie on the j omega axis, the system will become oscillatory. This is known as undamped, right? We are doing basically this theoretically. Practically, I have done this in the industry. We increase the proportional gain until the system becomes oscillatory, and then we measure the time period like this to this time, we measure it, and then we take its inverse, we get the frequency, then we multiply it with the 2 pi, we get omega. Omega is equal to 2 pi f. Okay, so this is a classical control method we are doing now. So here SQ coefficient, that is 1, and this is 23. Okay, and this is 9 and 15 plus 10k. So here you can see 1, 23, 9, 15 plus 10k. Okay, now the next column, how it is made? It is made through the root Harvard's table I showed earlier, that is minus 1 over 9, determinant 1 9 23 15 plus 10k. So you multiply this minus 23 into 9, and then the minus which is outer side, it is inserted in, so you will get 23 into 9 minus 15 plus 10k over 9. So this is the final term you get, and the further term is 0 because there is 0 0 here. And similarly, how do you get this term? You get this term by this, you say this is some capital A, then minus 1 over capital A, 9 capital A, 15 plus 10k 0, and then you solve, you will get this term 15 plus 10k. So this is the root Harvard's table you got, s cube s square s1. Now you have to make one row 0, so we make this row as 0. Okay, so when we make this row 0, it means 23 into 9 minus 15 plus 10k over 9 equal to 0. Okay, 9 goes to this side and becomes 0, we get this term, and if you solve this step by step, you will get the answer 192. Okay, so this is the gain, 192 is the gain at which your system will become oscillatory. For example, practically you start with gain 0 1 2, you have a potentiometer like knob, you are increasing its knob, you are rotating it on the clockwise, and then when it becomes 192, your system will become oscillatory. So after oscillatory, you measure its time period and then take its inverse frequency multiplied by 2 pi, you get omega. But you can also do theoretically here. How you can do theoretically? So this is this will become 9s square plus 15 plus 10k into s square. So you will get 2 decrement here, so s raised to power 0, that is 1. So 9s square plus 15 plus 10k raised to the power s raised to power 0 equal to 0. Okay, so this is you put here, and then you make s is equal to j omega. You can put here s is equal to j omega, or simply you can solve it here, put the value of 192 here, and then you will get this answer, and then you solve it further, you will get s is equal to plus minus under root 23. Okay, under root 23 j. Why j? Because of the minus term, and plus minus 4.8, that you get S. Now you know that S is equal to sigma plus j omega. If you make sigma 0, you will get only S is equal to j omega. So j omega is equal to plus minus 4.8, j cancels, and you get omega 4.8. So this is your omega. Omega is 2 pi f, or 2 pi over capital T. Okay, you know that we have omega is equal to 2 pi f, and 2 pi f is equal to, you know that, 1 over capital T. This is the time period. This is the ultimate time period you want to calculate Tu. Okay, so here we calculated it with the 2 pi over omega, that is 1.31 second. So these are the terms you want to know. Ultimate gain, that is 192, and the ultimate frequency and ultimate time period. You want to know these two terms, Ku and Tu. Okay, so how did we get it? First of all, we converted the we started with the proportional controller only. GPID we set it to K, and then what we did, we got the closed loop transfer function T of S like this, and then we picked its denominator. Okay, and then we made its root Harvard's table. After making the root Harvard's table, we made one row 0, and from here we got the value of K, the gain at which our system will become oscillatory, right? So this is how we get this K and capital T. So this is the first part we completed, the ultimate gain and the ultimate frequency. Now second part is the control tuning parameters using a P controller. So if you just want to make there is a difference between PID controller. P controller, it increases your rise time and your, but there remains some steady state error. How do you remove the steady state error with the I controller? And if you want further to improve your transient response, you want to reduce your overshoot, or you want to so we go to this table. This is the appendix table. If we want to simple proportional controller, we will just put 0.5 into Ku. Okay, 0.5 into Ku. What is Ku? 192. So 192 into 0.5, or half of the 192. This will be your P controller value. And if you make a PID controller, you just need to 0.6 into Ku. That will be the Kp part, and Ti part, it will be Tu by 2, and Td part, it will be Tu by 8. So you will have to calculate Kp, Ti, Td, and this is the equation for the PID controller. Kp 1 plus 1 over Tis plus Tds. So if you put these values after calculating, you will get the transfer function of the PID controller. So this is using the P controller, you get 0.5 into Ku, and this is 96, and Ti will be infinity and Td will be 0. And for the PID, you will make 0.6 into Ku. Okay, and Ti is your Tu by 2, 0.655, and Td will be Tu by 8, 0.16375. So this completes our first part of the first question. Okay, the part A. Now we will do the part A. A closed loop unity feedback system as shown in question 1A, okay, has a root locus as shown in figure question number 1B. So this is the system. Okay, its root locus is given here. This is the root locus of that system. It has 3 poles at -3, -4, and -15. So this is K over S plus 3, S plus 4, S plus 15. For this given system, determine the open loop poles. The open loop poles, we make the denominator here equal to 0. Okay, make the denominator equal to 0, you will get the poles, open loop poles. These are the open loop poles, right? G of S is the open loop transfer function. So it will be S is equal to -3, -4.
Okay, so we will get -3, -4, and -15.
Yeah, negative 15 minus
in the open
3
loop mode.
minus, yeah, equal to, make it equal to 0. Okay, make it equal to 0, so it
Yeah,
will
yeah,
be,
I know.
yes, make it equal to 0, you will get s plus 3 equal to 0, s plus 4 equal to 0, s plus 15 equal to 0. So then you will get s is equal to minus 3 minus 4 minus 15. Okay,
Okay,
so
then we graph the root locus, right?
yes, it's already given in the question. The root locus is already given, minus 3 minus 4 and minus 15. This is the
Mhm.
root locus they have already given you. Okay, and this is the these are the your branches, and this one goes to the infinity. Okay, because and it a root locus at, it starts from the pole and ends at the 0. So this is basically, these zeros are up to infinity. Okay, so coming back, the open loop poles will be minus 3 minus 4 and minus 15. The gain, second part is the gain k if the system operates in the critically damped condition. This is a very important condition concept, critical damped condition. What is critically damped condition? Critically damped condition will occur when we have all the poles at the same point. How is it is possible? I show you here. You can see that here. Here you can see this is critically damped. Okay, critically damped, it becomes possible when you have all both poles at
Will
the
those
same
graphs
location.
be in the will those graphs be in the exam, like in the appendix?
So for the critically damped, you need your poles to lie here in between minus 3 and minus 4. So this will be minus 3.5. So the system operates in the critically damped, then s is equal to minus 3.5. That's the reason, minus 3.5. Now we know the position of the poles when we want to operate our system in critically damped, but we want to know the gain. So how we will determine the gain? Its formula is k is equal to 1 over cs magnitude, the inverse of the transfer function, because the concept is k into cs equal to 1. This is the concept of the root locus concept. If I show you the root locus concept, so this is the root locus summary. Branches equal to poles, symmetric about the real axis. The real axis segments are to the left of an odd number of finite. We will cover these step by step. And root locus begins at the poles, ends at the 0, and this is the sigma a intercept, and this is the angle theta. The breakaway and break-in points from the real axis, and the imaginary crossings. So here you can see that k into g of s into h of is equal to minus 1. So that's the condition. For the magnitude, it will be equal to 1 and the magnitude. So this is how we will get the gain k. Okay, now coming back to our question. Our question is the gain k if the system operates in the critically damped condition. So for the critically damped condition, we want our poles to lie here at minus 3.5. So s is equal to minus 3.5, k is equal to 1 over magnitude of cs, 1 over cs. So cs here, g of s, basically the transfer function. So 1 over gs will be its inverse. Okay, so that will be s plus 3 into s plus 4 s plus 15 magnitude. Put s minus 3.5 here, so you will get minus 3.5 plus 3, you will get minus 0.5, minus 3.5 plus 4, we will get 0.5, minus 3.5 plus 15, you will get 11.5. Okay, you have to put this minus 3.5 here, and then you have to multiply all those, and then this minus sign will get cancelled because of the this absolute or mod. You will get 2.875. So this is the gain. 2.875 is the gain at which you will get your critically damped system, and your response will be critically damped, like this one. this one, this is the your response will be like this, critically damped condition. Okay. Okay, now we move to the next part. Find the range of the gain k if the system operates in the underdamped region. So this is another important concept, underdamped. So for the underdamped, this is your underdamped region from this to this here before the imaginary axis, because at imaginary axis your system will become undamped or oscillatory. So we have to calculate the gain before this point, this point at which it crosses your g omega. So this is the region basically where your system will operate in the underdamped region, because your poles will move to the g omega axis. Underdamped means you have both real part as well as imaginary part, like this. This is your underdamped, basically underdamped. You have some oscillations, okay, as well as your some damping. There is some damping as well as oscillations, zeta between 0 and 1. So and these will be the poles. So this is the region from this to this where your system will be the underdamped, right? So we will move to the solution here, how underdamped. So here how you will know the range, you get the extreme value, you find the value of k here, because at this gain your system will move away from the underdamped to undamped. So you find this gain. So this is your s is equal to 11j approximately. It's approximate, it's not exact, it's approximately 11j. So put s is equal to 11j here, s plus 3, s plus 4, s plus 5. Put 3 plus 11j, 4 plus 11j, 15 plus 11j. Okay, now you have to calculate this by calculator. You put 3 plus 11j, put your calculator in the your complex number mode, and then calculate this, multiply all these, multiply, after multiplying all this you get it this magnitude 2482. Okay, so at 11j, what, why 11j, 11j, why 11j? Because at this 11j your system will be will move to another domain, that is undamped. Okay, so this is the extreme value. So what is the gain at this extreme? 2482. So this is the gain, this is the gain. Your system will become oscillatory. So your system will operate in the underdamped region from this to this, like from 2.875 up to 2482. You can move, increase the gain up to this. Your system will be underdamped. But if you make your gain 2482, your system will become undamped. So here you see that k greater than 2.875, less than 2482.4. Okay, so this is the range at which your system poles will move here. Okay, your system poles will move here, and your system will be in the underdamped region. Or you can say that k greater than 2.875, but its upper limit is this. You have to make your gain lower than this, because if you make your gain equal to this, your system will become undamped, and if you make your gain greater than this, your system will become unstable. This is the unstable. On the right half plane your system will become unstable. Okay, so next part is using the second order approximation, determine the value of k to yield 10% overshoot for a unit step input. Now we have to calculate the value of k to yield 10% overshoot. Now this is the percentage overshoot. Remember, from percentage overshoot we will be able to get zeta. Zeta is the damping ratio, and from zeta we will be able to get theta. Theta is the angle. So what are these things I show you here? So percentage overshoot, that's given, that's what is given, 10%, right? So e raised to the power minus zeta pi over under root 1 minus zeta square into 100. Or if we want to calculate the zeta, how we will calculate it? From this formula. Basically it's inverse of that formula. We get minus natural log percentage overshoot over 100 over under root pi square plus natural log square percentage overshoot over 100. So your overshoot is 10%. Put here 10 over 100, 0.1, here 10 over 0.1, and calculate this. You will get your zeta. Okay, so here you can see that we get, for the percentage overshoot 10%, we get zeta 0.591. okay, and how we'll get theta? By taking its cos inverse of 0.591, because zeta is equal to cos theta, and theta will be equal to cos inverse of zeta. You can see here, look at this percent. This is for example for the 20%, we put here 20, you get zeta, and then if you make cos inverse of zeta, you get theta. Okay, so it's here percentage over e raised power minus pi zeta over under root 1 minus zeta square. So here you get this answer as zeta 0.5911. so here you have 0.591. okay, and then you take its cos inverse, you will get this angle. Okay, so now this angle is 53.76. This angle is 53.76. I show you the meaning of this angle. So this is the angle, basically this is the theta, basically you get is theta, this is theta, basically this angle is theta. So here theta is 53.76. so here you can find your pole when you have 10% overshoot. When you have 10% overshoot, there will be 53.76 angle from here. So you can measure from your D or campus. So that will be 53.76. Here you get like something near here. So these will be your poles. So these are some rough they have written here. minus 3 plus 3j here. minus 3 plus 3j and minus 3 minus 3j complex conjugate. This will be in complex conjugate. So minus 3 is the real part, minus 3 plus 3j, minus 3 minus 3j. So this is minus 3 plus 3j. These will be the dominant poles, plus minus 3j dominant poles. And now how to find the gain at this point? Simple, k is equal to 1 over gs magnitude. Put here just here put minus 3 plus 3j. When you put minus 3 plus 3j, minus 3 will be get cancelled, you get minus 3j, and here you will get 1 minus 3j, minus 3 plus 3j. So here you will get 1 plus 3j, and s plus 15. Put this minus 3 plus 3j here, you get 12 plus 3j. So you need to solve that thing. Then after solving this, I did this on my calculator. It's okay, it's written as it's perfect. This okay, this comes to be 117.35. so this is the gain at which you will get 10% overshoot. Okay, you will get 10% overshoot here. minus 3 plus 3j minus 3 minus 3j. So this is a very important concept from this. Okay, so you get from percentage overshoot, you got this zeta. How did you get this? You get from the formula here, right? Okay, this is the formula. It will be given in the appendix to you. Percentage overshoot formula. Where is it? This is the formula. Okay, this is the zeta. So zeta, and from this theta, how did you calculate? By cos inverse. Cos inverse of 0.591, you will get 53.76 in degrees. And from this theta you got minus 3 plus 3j. Okay, and if you put this here, you will get your gain. So if your gain is 117.35, you will get 10% overshoot. Okay, so determine the value of k to yield 10% overshoot for a unit step input. It's done. Determine the settling time, peak time, rise time, steady state error. Okay, now settling time, it's well defined formulas. You know that its formulas are very well defined. This is your peak time, pi over omega d. Omega d is your imaginary part. This is your omega d, imaginary part, right?
So should we memorize those rules?
So determine the settling time. It will be, now these are the poles, -3 plus 3j and -3 plus minus 3j. Basically these are the poles at which you will get 10% overshoot. So your settling time will be 4 over your real part, that is 4 over zeta omega n. So zeta omega n is the real part, this is zeta omega n, okay, and this is your omega d. Omega d is equal to omega n under root 1 minus zeta square. So 4 over real part, that will be 4 over 3. So 4 over 3 will be 1.33 seconds. And peak time will be pi over omega d or pi over imaginary part. So pi over 3, pi over 3, that will be 1.04 second. So you must write the correct units here. Time, for the time you have the unit seconds. And for the steady state error, this is a type 0 system. This is a type 0 system because there is no pure integral. Type 0 means s raised to the power 0. Type 1 means s raised to the power 1. One integral, one pole at the origin. S raised to the power 2 in the denominator. It means type 2 system. So this is a type 0 system. Its steady state error formula is 1 over 1 plus kp. And kp is equal to limit s approaches to 0 g of s. So if you put this g of s, put limit s approaches to 0, make this 0, this is 0 0, you will get 3 multiplied by 4 multiplied by 15, and k, put this value of k, what is k? 117.35. So 1 over 1 plus 117.35 over 3 into 4 into 5, you solve this and you will be get steady state error, that is 0.6053. And what is your rise time? It's not done here. It will be 2.2 over real part. So it will be 2.2 over 3, 2.2 over 3. Okay, this will be your rise time, and 4 over 3 it will be your settling time. Okay, this is a generic formula, 4 over tau, and this is 2.2 over tau. Okay, so this is your question which is completed, part 2. Now we come to the part 3. Use second order approximation, determine the validity of the second order approximation. So what is this? You can see the pole. First see the pole. This is one pole is at -3, one pole is at -4. So 15, this pole is bit near to 4, so second order approximation will not be valid. As -15 is less than 5 times, 5 times means 20, this pole should be away from 20, like s plus 21, s plus 22, then you can ignore this pole and you can approximate the system as a second order system. Then the approximation will become valid. At this stage the approximation will not be valid. So as -15 is less than 5 times the left pole -4, so the second order approximation is not valid. Okay, second order approximation will not be valid. The pole should be at least away from the 20, s plus 20. If it's away from the s plus 20, it will be valid. We can ignore this pole, but right now we cannot ignore this pole. Okay, next one is sketch the response of the root locus if 0, s is equal to -5. So this is s plus 5 equal to 0. 0 is added into the transfer function. So if you add a transfer function s plus 5 here, a 0 at -5. Okay, so what will happen? So here you can see that this is the original root locus. Now you are adding a 0 here, you are adding a 0 here. So you know that, we know that a pole ends at some 0, and the root locus will be on the left side of the odd number of odd number. So this is the odd number 1, the root locus will be here 2 and 3, this will be root locus something here. So if we put a 0 here, this pole will terminate at this 0. Okay, and this will remain the same here, it will remain the same. So here you can see that -3 -4 it remains the same, but this 15 it will be terminated at this 0, because this is the rule of the root locus. I show you the rules of the root locus. This is the rule of the root locus. that real axis segments are to the left of an odd number of real axis finite poles and zeros. Odd number, it will be to the left of the odd number, and root locus begins at poles and ends at zeros. So here you can see that the root locus from the odd number 1 is odd, so here will be root locus, yes. 2, no, there will be no any root locus. 3, yes, there will be root locus like this 15 will be terminated at this 0. So this is the new root locus. If you add -5, s is equal to -5, or s plus 5 equal to 0, this is a 0 is added here, so it will become this. So this is the answer to this question. Sketch the response of the root locus if 0 is added into the transfer function. So if you add a 0 here, you will get this root locus. This is the revised root locus you will get. So this completes our question 1 for the feedback control theory. Thank you.